today's workshop, we will be finishing off our introductory material on acids and bases. For the first question that we're going to look at today, let's draw the conjugate base for the following acids. Okay, so I'm going to draw an acid here. Let's take acetic acid, the main component in vinegar. Add a few lone pairs here and here. And let's draw the conjugate base for this. Remember, to draw the conjugate base, we have to simply remove the most acidic hydrogen. So that's going to be this hydrogen that is circled. Why is that hydrogen the most acidic? Well, because when that hydrogen leaves, it leaves behind a very stable negative charge, which is resonance stabilized. Okay, we'll see that over here. It's also attached to an oxygen, and remember, oxygens and other highly electronegative or large atoms are very stable with a negative charge. Okay, that makes any hydrogens attached to them typically more acidic. So this negative charge on the conjugate base is resonance stabilized. We can draw a resonance structure here. Looks like that. We'll move the double bond up to be a lone pair, and we can bring a lone pair down to be a double bond. So there's resonance occurring here. We have a lone pair in the allylic position adjacent to a double bond. So we have these resonance structures we could draw, which makes this hydrogen very acidic. Okay. So this would be the conjugate base of acetic acid. We simply remove that hydrogen that's circled. We remove that acidic hydrogen. Okay, what about for this structure? What if we have just a simple phenol? That's a OH attached to a benzene ring. What's the conjugate base for this acid? Well, we simply remove the most acidic hydrogen. Again, it's going to be this hydrogen because it's attached to oxygen, a very electronegative atom. And because if we have a negative charge at that position, it's in resonance with the rest of the ring. So the conjugate base would simply be this structure here, the negative charge. Okay, pretty straightforward so far, simply removing the most acidic hydrogen. What if we have a structure like this? Six-membered ring with a C double bond O. What would be the conjugate base of this structure? We don't immediately see any really acidic hydrogens, any OHs, or something like that. So where is the most acidic hydrogen? Let's look at a few. Let's draw some in here. Now this is a symmetrical molecule, so the hydrogens on the left and the right should be pretty much the same. We'll talk about hydrogen equivalency in a future chapter, but let's just consider some of the possible hydrogens we have on this molecule. If we removed maybe any of these hydrogens down here in red on these two carbons, right? If we had a negative charge down there, that would just be a regular old negative charge on a carbon. Let's draw what that would look like. We could put a negative charge maybe down at this position. And this is just your regular old negative charge, right? If we took off maybe this red hydrogen here that I circled, or if we put a negative charge at the very bottom position, it doesn't matter. Either way, that's just your standard negative charge attached to a carbon. So that's going to be a pKa around 50. These hydrogens down here, they have pKa's around 50. Because this is just a CH, a sp3CH bond. There's nothing special about it. It doesn't partake in resonance. There's no induction. There's nothing affecting these CH bonds to make them particularly more acidic. However, if we deprotonated this blue hydrogen, one of these blue ones here, or it could be on the other side of the carbonyl, any of those hydrogens, these blue hydrogens have a much lower pKa. These hydrogens have a pKa around 19. Okay, these hydrogens have a pKa around 19. Why do these blue hydrogens have a pKa around 19 instead of around 50? They're CH bonds. Well, because they're adjacent to that carbonyl, right? If we deprotonated one of those blue hydrogens, if we removed one of these blue hydrogens, maybe that one that I circled there, we'd have a negative charge at this position adjacent to the carbonyl, meaning that it can partake in resonance, meaning that it's more stable. So we could draw these two resonance structures if we were asked to. We could put a negative charge up on the oxygen, put a double bond down here. These would be two resonance structures we could draw. Okay, but this resonance explains why the neighboring hydrogens to a carbonyl are more acidic. These resonance structures show that that negative charge is going to be stabilized. Okay, so that's why these neighboring CH bonds to carbonyls are more acidic. So this would be the resonance structure. This would be the conjugate base. Okay. And maybe one more simple example. What's the conjugate base of H3O plus? If we remove an acidic hydrogen, now if we have H3O plus, we'll draw the structure out like this. One lone pair, positive charge. Doesn't matter which of these three hydrogens you take off. Okay, you could grab any one of them, and you would be left with H2O. Okay, conjugate base of H3O plus is H2O, simply removing a proton. Okay, let's draw some conjugate acids now. What if we have NaOH? What if we see NaOH as a reagent on the left side of the equation and it's acting as a base? What would it look like on the right side of the equation? Remember, when we see NaOH, we see a plus on sodium and a minus on oxygen. That's an ionic bond. It's between a metal and a nonmetal. Okay, so we can think of this as plus and minus. So if this is acting as a base in some chemical reaction, that means it's going to be grabbing a proton. It's going to be gaining a proton. Remember our Bronsted definition. A base is a proton acceptor. So the conjugate acid of OH minus would be H2O. We're gaining a proton. The sodium, remember, is just a spectator ion, okay? Just a spectator ion. It's not going to do any chemistry typically. So the conjugate base, the conjugate acid of this OH minus will be H2O. Okay, what about this alcohol here? We have isopropanol or isopropyl alcohol. What would be the conjugate acid of this alcohol? Well, if this is acting as a base, it's going to be accepting a hydrogen. Where could it accept a hydrogen? Well, remember, bases typically grab a proton using a lone pair. So the only lone pairs that we see here are on oxygen. So I circled one there. So this could grab a hydrogen, right? That's the definition of a base. And if it does so, it would become positively charged. We have oxygen with 3 bonds and 1 lone pair. So that would be the conjugate acid. Okay. Let's do one more example here, just sort of as a warm-up. These I know are probably pretty simple, but just to get your memory going as to what acids and bases are. What would be the conjugate acid of this anion? Well, if this was acting as a base, it would grab a hydrogen. It would grab a proton. And so we have 2 options here. We could add it at the negative charge, or we could add it at the oxygen. And it's going to be preferred to add at the negative charge down here. Okay, this negative charge is much less stable. It wants to fulfill, it wants to grab a hydrogen much more than this oxygen does. If you have a negative charge, that's typically going to be the spot that acts as a base. Okay, so if that acts as a base, grabs a hydrogen, that just puts a CH bond there. Okay, over here we have a CH3. And on this carbon here, we just have 2 hydrogens and then that negative charge. So if we grab another hydrogen, that gives us a CH3. You could just leave it like this, or you could write the CH3. Either way, what we're left with is just acetone. That would be the conjugate acid of the negative charge, right? Here's the base, and here's the conjugate acid. Okay. All right, now let's step it up a notch. Let's now consider a few different compounds and determine which is more acidic. And to do this, we can use pKa, or we can do a qualitative analysis using ARIO, using our analysis of the atom, resonance, induction, and the orbital. Okay, so whichever method you prefer, or if you want to practice both, that would be ideal. But either way is good. Again, if you know the pKa values or you have a chart, that's probably more easy. That's probably easier. However, understanding the qualitative analysis is also very important and can definitely help you for unique molecules. So let's compare phenol to cyclohexanol, these 2 molecules here. Which one is more acidic? Well, I think it's pretty obvious that we are comparing the hydrogens in blue, right? We have an OH over here and we have an OH over here. Remember, anytime we're connected to a very electronegative atom like oxygen, that's typically going to be the most acidic hydrogen. Now on the left, let's start with our qualitative analysis. On the left here, if we form a negative charge at this position, we know from previous examples, and just by looking at this molecule, that if we form a negative charge up here, right, on this oxygen, it would be in resonance, right? We could draw resonance arrows throughout the ring system, indicating that that's going to be a nice stable negative charge there. If we look at the right, there's no resonance occurring whatsoever. So that means All other things are equal, right? It's OH, OH, same structure otherwise. The only difference are these double bonds. These double bonds allow the resonance to take place. That's the R in ario. So if we have resonance, we have a more stable negative charge, which makes this phenol with the double bonds more acidic, right? Let's look at the pKa values just to be sure. Okay, the pKa of phenol is right around 10. And the pKa of cyclohexanol, just your regular old alcohol, is somewhere in the neighborhood of 16, 17. Remember, lower pKa is higher acidity, it's more acidic. So therefore, our pKa values agree that the phenol is more acidic than the cyclohexanol. Okay, so either way, you can use pKa or you can use ario, whichever way works for you. What about these two here? We have cyclohexane, and then we have NH2 connected to the ring. Instead of OH like last time, we have an amine, NH2. This is cyclohexylamine. And let's compare that to a triple bond. Six-membered ring with a triple bond. So the first step is to identify what's your most acidic proton, what's your most acidic hydrogen. In the case on the left, it's going to be the NH2. We have two hydrogens on that nitrogen. That's going to be more acidic than, say, these CH bonds, because remember, carbon is less electronegative than nitrogen. So NH2 versus, and then our most acidic hydrogen over here is on the terminal position of the triple bond. Remember, the triple bonds are much more acidic than the double bonds or the single bonds. Okay. Okay, so comparing these two, let's first start with our qualitative analysis. Okay. Start with our qualitative analysis. Now, this is an example where the qualitative analysis may be a little tricky because we have multiple facets to consider here. Okay. Let's first consider the atom in question. We're comparing a nitrogen, an NH, versus a CH. Okay. Typically, NH bonds are more acidic than CH bonds, right? So just considering the atom, it seems like the cyclohexylamine on the left should be more acidic. Okay. Let's look at resonance. There's no resonance occurring here, right? There's no adjacent double bonds here, so we don't need to consider resonance. Induction, there's no induction occurring here. However, we can consider the orbital. Okay, the NH2, this is going to be in an sp3 orbital. Okay, this is just your standard tetrahedral nitrogen, so sp3 hybridized. The CH is in an sp orbital, sp, because it's on a triple bond. And remember, the triple bonds are much more acidic than double or single bonds because we have more S character. So that negative charge is closer to the nucleus and more stable, right? So this is a case where we actually have some competition here. The atom prefers the NH bond, however, the orbital prefers the CH bond. So this is one where you sort of have to understand pKa values, because using our ario rules, you can't really make a determination since there's competition between the two here. So let's look at our pKa values. For an amine, something like ammonia, it's going to be in the mid to upper 30s. Ammonia is about 38. Okay, so NH2 is not going to be far away. So somewhere around 38. We know that from our chart. And if we look at our chart for the triple bond, we see that a triple bond pKa is somewhere around 25. So it actually turns out that the orbital is more impactful here than the NH bond, right? Having an sp orbital gives a stronger acid than having an NH bond, okay? So for this one, you kind of had to use pKa's, or at least understand that triple bonds are more acidic than amines, because we have some competition using our qualitative analysis, okay? So looking at pKa's, it's much more clear. The triple bond is much more acidic with a pKa around 25. And what about this one? Let's look at one more here using this format. Let's take a double bond acetone versus this ether. Okay, so we have this ether versus this carbonyl here, this acetone. So what's the most acidic hydrogen in either case? Well, if we recall from our previous example using acetone, the neighboring CH bonds are the most acidic, right? Now, these are the only CH bonds we have, are the ones adjacent to the carbonyl. So obviously we'll be removing one of those CH bonds. And on the ether, again, it's going to be one of these CH bonds. Now, it doesn't matter which one you choose. It could be any of these CH bonds. All of these terminal positions have 3 hydrogens on them. It doesn't matter which carbon you grab from. They're all equivalent. Remember, atoms, bonds, they're always moving through space, rotating, twisting. So it doesn't matter. I'm drawing the molecule like this, but it doesn't matter exactly how you draw it, right? All of these carbons at the end of this chain here are equivalent because they have the same connectivity. They have the same relative connectivity. So it doesn't matter which of these hydrogens you select, okay? Likewise, it doesn't matter which hydrogen on acetone on the left here you select. It could be either this blue hydrogen on the left or this blue hydrogen on the right, okay? If that doesn't quite make sense to you right now, that's okay. We'll talk about hydrogen equivalency in a future chapter some more. But let's just look at these CH bonds. Let's look at the ones in red. Let's take this hydrogen and this hydrogen and figure out which one is going to be more acidic. Let's look at a qualitative approach first. They are both CH bonds, CH on the left, CH on the right. So the atom doesn't help us. What about resonance? On the left here, we have resonance, right? Because if we have a negative charge there, it's adjacent to a double bond. But on the right, there's no resonance. No resonance on the right, right? There's no double bonds on the right. So if we make a lone pair here, it's not in the allylic position. We can't do resonance, so it's not resonance stabilized. There's no induction we have to worry about, and they're both in the same sp3 orbital. So the only difference here is that the left is resonance stabilized, but the right is not. So therefore, the left should be more acidic. And let's double check with pKa values. The pKa of a hydrogen adjacent to a carbonyl is around 19. And the pKa of just a regular old CH bond is around 50. Remember, that's the least acidic thing we could have. It's just a regular sp3 hybridized CH bond. All right. So obviously the one on the left here, pK 19, is much more acidic as compared to the one on the right. Okay. Okay, now let's quickly practice a little bit on finding the most acidic proton. Let's take OH, carbonyl, OH, draw some lone pairs. Now, which hydrogen is most acidic? So let's first look at all of our hydrogens and maybe we'll color code them. We have this OH on the left in red, the OH on the right in blue, and then in green we have these two hydrogens here, right? Now, what you could do here, I think the easiest way is to go through and just sort of give a pKa number to each set of hydrogens, okay? That will allow you to figure out what the most acidic proton is because the one with the lowest pKa is going to be most acidic. You could also apply our ARIO qualitative analysis rules, try to figure out which one's most acidic. But I think applying pKa is probably going to be the most straightforward. So let's work through here. The green hydrogens, if we have hydrogens adjacent to a double bond, right? Think of the previous example we did. Those pKa's are around 19. Around 19. I'm putting a little tilde here indicating it's around 19. That's not a negative. I'm just saying it's somewhere around in the neighborhood of 19. This red hydrogen, this is just an OH. It's not partaking in resonance because there's this sp3 hybridized carbon in between it and the double bond. So this is simply a OH, and we know alcohols are in the neighborhood of 16 to 18. So I'm going to put somewhere around 17 for that one. And then what about our blue hydrogen? The blue hydrogen here is part of a carboxylic acid. That's an OH connected to a carbonyl, a C double bond O. This blue hydrogen is around 4. This blue hydrogen is much more acidic because it's connected to an OH, and it's also in the allylic position, right? This negative charge that would be left over is in the allylic position, so it's resonance stabilized. So the blue hydrogen here is part of the carboxylic acid, which is going to be clearly the most acidic hydrogen on the molecule. So if we did an acid-base reaction, if we added a base to this molecule, which hydrogen would leave? The most acidic hydrogen, which is this blue one. So what would we be left over with? If we treated this with a base, we would have negative charge there, and the rest of the molecule would stay the same. So that would be the product after treating that molecule with a base. Okay, you remove that most acidic proton. Okay. Okay. So looking at the next example here, let's consider, what if we had a 6-membered ring, double bond here, triple bond here. So this is just a hydrocarbon. All we have is carbon and hydrogen. What's the most acidic proton? Well, when we have this example, we should remember that triple bonds have that very acidic hydrogen, right? If we have a triple bond with a hydrogen, that has a pKa around 25. Much more acidic than if we have a double bond with a hydrogen, which is around 45. And if we simply have a CH bond that's sp3 hybridized, that would be around 50. So just by looking at our orbitals, sp, sp2, sp3, right? Because we just have hydrocarbons here. We don't have any other atoms. We just have carbon and hydrogen. Our most acidic proton is going to be this one in red, this CH, because it's attached to a triple bond, right? The blue ones here would be next up. Those blue ones are around 45. And then all the other hydrogens, the implicit hydrogens, I'll draw a few over here. All these CH3s and the CH2s over here, all the rest of these green ones are around 50. So those would be last, okay? But our most acidic hydrogen is that one right down there on the triple bond. Okay, and one more. Okay, and then for a final example for this problem, find the most acidic proton. What if we had OH, maybe a chlorine here, and double bond down here? What would be the most acidic proton? Well, again, let's break some down here. Let's take this OH up here. That's definitely a contender. We have some CHs down here on double bonds. And then other than that, we just have CHs on single bonds, right? sp3 hybridized carbons. So those are all the options we have. Okay. So what's going to be the most acidic hydrogen? Well, remember, alcohols have pKa's around 16 to 18. So we'll put somewhere around 17 here for the red hydrogen. For the double bond, this pKa is around 45, so much less acidic. And then for all these purple hydrogens, these are going to be in the neighborhood of 45 to 50. Now, these purple hydrogens that I circled, you may say, well, those are partaking in resonance. If we deprotonated those positions, those would be resonance stabilized. And that's true. That does make these circled purple hydrogens a little bit more acidic, lower towards 45, as opposed to 50. But either way, they're still much less acidic than an alcohol, okay? Again, anytime you have an OH, something attached to a oxygen, that hydrogen is going to be much more acidic than something attached to a CH, all other things equal, okay? So pK of 17, that alcohol there is going to be the most acidic portion of the molecule. That OH is going to be the first thing to react with a base. Okay. So again, if you're ever confused at which hydrogen is the most acidic, just break down the possible protons you have, write down some relative pKa's, and one should stand out as being the most acidic. Typically, it's going to be attached to an oxygen, either an OH, or connected to a carboxylic acid, right? A carbonyl adjacent to an OH, that's also a very acidic group. And remember your basic rules, ARIO, atom, resonance, induction, and orbital, okay? For the next problem here, it'll be multi-part. Let's draw a mechanism. Let's label the acid, the base, the conjugate acid, and the conjugate base. show the products of the reaction, show the equilibrium, and explain why that equilibrium is as you've shown. Okay, so multi-step here. Let's start off with this one. Let's take H2O. Okay, let's take water. And let's add to it this negative charge. So this is clearly going to be the base. Okay, let's draw a mechanism and show the products of this reaction first. So what would be a mechanism for this acid-base reaction? Well, we'll take a lone pair on our base, which is obviously going to be the thing with the negative charge here. Draw a curved arrow to the proton, okay, onto the acid. We're going to take that proton and leave behind the electrons in that OH bond as a lone pair on oxygen. Let's draw some standard equilibrium arrows for now. And the product is going to then be OH minus, right? We took a hydrogen from water. And the product, our isopropanol, the anion has now gained a hydrogen to just become isopropanol, right? We've taken a hydrogen, so now that's neutral. Our negative charge is now on the hydroxide. Make sure your charge is balanced. Okay, we have a negative charge on the left, negative charge on the right. Okay, so that looks good. Let's label the acid, the base, the conjugate acid, and the conjugate base. Obviously, this is our base. It's negatively charged. This is the acid. It's donating a hydrogen, donating a proton. For the reverse reaction, this one over here would be the base. So therefore, this is the conjugate base. Again, negative charge, base. If you see a negative charge, that's probably going to be your base. And isopropanol would be the conjugate acid. Okay, now let's predict which side of the equilibrium is favored and draw some proper equilibrium arrows. Remember, to do that, we need to compare the pKa's of the acid and the conjugate acid. The pKa of water, 15.7. The pKa of isopropanol or any other alcohol is just above water, 16 to 18. So we'll say somewhere around 17. Doesn't have to be exact because either way, the pKa is going to be higher on the right, whether you put 16, 17, or 18. I don't know the exact pKa of isopropanol, but as you can see, it's not necessary. Okay, you could look up the exact pKa of isopropanol if you wanted to, but it's not necessary. Okay. Again, you don't have to memorize absolutely everything. Okay, you just have to know a couple relative pKa values. But if you are allowed to use pKa charts on your exam, obviously that will just help you. Either way, pKa on the right is higher. 17 is greater than 15.7. So the equilibrium is favored. So the equilibrium is favored to the right, because remember, the equilibrium is favored to the side of higher pKa. The hydrogen is more happy at a higher pKa. So the equilibrium is favored to the right because we have a higher pKa. Okay. Okay, so there's the first example. Sort of a combination of everything we've looked at for the chapter. So these are good questions here. We'll do a few more of these. Okay, what if we had acetone plus NaOH. Okay, so this would be the second problem here. This is what we're given. Let's answer all these problems. Okay. Let's look at the forward reaction and the reverse reaction. Remember, when we have NaOH, what does that mean? It means we have a positive sodium and a negative oxygen. Na plus, OH minus. So obviously this is going to be our base. We have OH minus. That makes this our acid. This is our proton donor. What proton are we going to be donating? Obviously the only type of proton we have, which is the ones adjacent to that C double bond O. Mechanistically, a lone pair from OH is going to take that hydrogen, take that proton, and leave behind the electrons in that CH bond as a lone pair. What's that going to give us here? It's going to give us C double bond O with a lone pair, a negative charge on that carbon. And you could draw sodium over here if you wanted to. Right, sodium in this case is just a spectator ion. And then we have OH minus grabbing a hydrogen. What's that going to become? H2O. Okay, H2O. Again, you could just totally ignore the sodium. If you don't want to write the sodium there, that's fine. It's a spectator ion. It's not going to do any chemistry. Okay, for the reverse reaction, we have a negative charge here, so this is going to be the conjugate base. And water would be the conjugate acid. Now, which side of the equilibrium is favored? Let's compare the acid and the conjugate acid. The pKa of water is 15.7. The pKa of a carbonyl, an adjacent CH bond, is around 19. So therefore, the equilibrium is favored to the left, the side of higher pKa. Okay, the equilibrium is favored to the left, so we'll put a small forward arrow and a large reverse arrow, indicating that the starting material is preferred for this equilibrium reaction. The equilibrium is favored to the left because the pKa of acetone is higher than the pKa of water. The hydrogen is more stable. The proton is in a more stable position when attached to acetone as compared to water. Okay. Let's do one more of these. Let's look at this. This is going to be a sort of an interesting concept for us to look at. We have a negative charge on this nitrogen. We have an OH here. Okay, 1, 2, 3. Okay, so this is all we're given right here. Okay, so we only have one starting material. So this is different than what we've seen before. So what's going on here? This is going to be an intramolecular reaction. Intramolecular. Intra meaning in the same molecule. Okay, intramolecular. So that means our acid and our base are both connected in the same molecule. and the molecule is going to react with itself. Okay, so we see we have a negative charge here, negative nitrogen. That's going to be the base. And then we see we have this OH. That's going to be our acid. Okay, so what would the acid-base reaction look like? Mechanistically, the base is going to grab the acidic proton. It's going to leave behind its electrons as a lone pair. What's that going to give us? It's going to give us a negative charge on that oxygen. So we'll put 3 lone pairs and a negative. 3 carbons, and then nitrogen now has a hydrogen and a methyl group. So we've essentially switched positions of the negative charge and the hydrogen between the nitrogen and the oxygen. For the reverse reaction, this oxygen is now the base, so that would be the conjugate base, and the NH would be the conjugate acid. Okay? So now we have to determine which is favored, which side of the equilibrium is favored. So what we have to do is we have to compare the pKa of the acid, which is the OH over here. Let's draw it in red. We have this hydrogen, this OH is going to be the acid for the forward reaction. And for the reverse reaction, the conjugate acid is this NH. So comparing the pKa's, the pKa of an OH is going to be in the neighborhood of 17, and the pKa of NH is going to be much higher, right, in the range of 38. Again, you don't have to know exactly because there's such a stark difference here. Obviously, the reaction is going to be favored in the forward direction to the side of higher pKa. The amine, the nitrogen, is much less acidic than the oxygen. Therefore, the equilibrium is favored to the right. So the products would be preferred here. The negative charge would rather be on oxygen, right? That makes sense because more electronegative atoms are more stable with a negative charge. And looking at the pKa's, we can see that oxygen is much more acidic. Right? That means this hydrogen wants to leave when it's attached to oxygen much more than when it's attached to nitrogen. Okay, so a lot of different ways to think about that. Ultimately, the best way to think about these is to just write down your pKa values, figure out where that hydrogen is most stable, where that hydrogen is most acidic, and show that the equilibrium is favored in the direction of higher pKa. That means that hydrogen is more stable or more happy at that position of higher pKa. So for the final question of the workshop, this is going to be sort of a challenge question here. And there will be 2 parts. This is the first part. First, looking at this reaction below, let's show the products of this. Let's show the equilibrium. And let's decide if the reaction would work or go to products. Now, when we say would the reaction work, what we mean is the forward reaction favored to the reverse reaction? If we want to form the products, right, our goal is to form the products of this reaction, we have to determine if the reaction would favor the formation of the products. So we're going to be looking at that equilibrium arrow, okay? I just have some generic equilibrium arrows drawn here, but let's think about this. The most acidic hydrogen we have is on the triple bond here. Mechanistically, our base is going to grab that hydrogen and leave behind its electrons as a lone pair. The products of this reaction would thus be a negative charge on the triple bond and ammonia, NH3. Okay. Let's compare the acidity of the triple bond, which is around 25, to the acidity of the conjugate acid, which is ammonia, around 38. Therefore, the forward reaction would be favored because we favor the formation of the products with higher pKa, right? We favor the higher pKa, ammonia versus the triple bond. The ammonia has a much higher pKa, so therefore the products are favored in this reaction. Now the follow-up question here, which is sort of a challenge question, is would ethanol work as a solvent? Now we'll get into some nomenclature next time. Ethanol, if you don't remember, is 2 carbons with an OH. So we're asking the question, would ethanol work as a solvent for this reaction? So let's redraw this process with ethanol. Okay, so if we have this triple bond, I'll draw the hydrogen there, and we have this negative charge, this NH2 with a negative, and we have a bunch of ethanol floating around as solvent, what would happen here? So we have, you can think of a reaction vessel, right? A round bottom flask or something. And inside that reaction vessel, we have ethanol as solvent, right? That reaction vessel is filled partway with ethanol. And we have our reagents, which would be the triple bond in question, as well as our base. Now, the concentration of solvent is typically going to be higher than your concentration of your reagents, right? There's going to be much more ethanol than the base or the acid. Now, what would happen if we were to add together a base with a solvent that has an acidic hydrogen? I'm going to draw ethanol again above. Ethanol has an acidic hydrogen with a pKa around 16. Now, this is going to be a problem for our reaction. If you can think about this, if we add a base together with a solvent that's acidic, what's going to happen? Well, an acid-base reaction is going to occur. And you have to be cognizant of the fact that solvents can react with your reagents, okay? Now let's draw this process out. Let's for a second ignore our triple bond reagent, and let's just consider what would happen if our base was to react with our solvent. We would get this equilibrium where we're given NH3 plus ETO minus. ET, by the way, stands for ethyl, which is simply a 2-carbon chain right there. Okay, I'm just abbreviating it ET. That's often how you'll see ethanol written out. Now you could also draw it like this, OH and O minus. That's perfectly fine. If you want to do that, feel free. So this would be the equilibrium reaction between NH2 minus and ethanol. Comparing the pKa's of our acid and conjugate acid, we have a pKa around 16 and a pKa around 38. So this reaction is strongly favored to products. So therefore, if we have ethanol as a solvent, this is what we really have floating around in our reaction vessel. We have ethoxide, the anion of ethanol, with ammonia. Now we have to ask the question, is ethoxide a strong enough base to deprotonate our product, our triple bond? So let's go back. I'm going to erase this here. And let's now draw the same reaction, but with ethoxide. If we have our triple bond here, but instead of NH2 minus, we have ethoxide, would this reaction work? Well, what would the products look like? It would have a negative charge on the triple bond plus ethanol. And what are the pKa's of our acid and conjugate acid? 25 versus around 16. The reverse reaction is favored. Therefore, this reaction would not work with ethoxide. So again, if we used ethanol as a solvent, ethanol in conjugation with our two reagents up on the top right, we have our triple bond and we have our NH2 minus. The NH2 minus is not going to ignore the ethanol, right? Molecules don't have brains and they can't think about what to react with, especially for acid-base reactions, which are very quick. If a base touches an acid and it has a good productive collision, which it most likely will, then a reaction will occur, okay? So if that NH2 even touches an ethanol, it will react with it to produce ethoxide. And that is going to be essentially an irreversible reaction because the pKa difference is so large. So we don't really have NH2 minus floating around in the pot. What we truly have is ethoxide. And this ethoxide is just not strong enough of a base in order to deprotonate this triple bond. And we can figure that out by drawing out this reaction and looking at the pKa's, seeing a stark difference between them, and realizing that this base, ethoxide, this O minus, is just not strong enough to deprotonate that triple bond, okay? The reverse reaction is favored, not the forward reaction. So what did we learn from this problem? Well, we learned that you need to be cognizant of the solvent in the system, and you have to pick a solvent that doesn't have an acidic hydrogen associated with it for many reactions. If you have an acidic hydrogen on your solvent, it can cause a variety of issues, particularly if you're doing an acid-base reaction. Okay. If you have a solvent that has a hydrogen on it, we call it a protic solvent. And if you have a solvent that does not have a hydrogen on it, an acidic hydrogen, we call it aprotic. Protic versus aprotic. Okay, so that's a good consideration when you're setting up chemical reactions. You have to be cognizant of the fact that your solvent can have an effect on the reaction, particularly in this case, if you have an acidic hydrogen on your solvent, it can impact acid-base reactions. Okay, so this was definitely a challenge question, but if you could follow along or solve it yourself, you're in great shape. And that's everything for acids and bases. Pretty straightforward chapter overall. Again, you have to either use pKa values or use ARIO to qualitatively solve whether something is a stronger or weaker acid. The next chapter we're going to begin, we will be looking at nomenclature as well as hydrocarbons. We'll be talking about hydrocarbons as well as their conformations that they can adopt. Okay, thanks for joining me for this workshop, and I'll see you in the next video.